You can see it, right?
Yes, it's visible, yeah.
Okay. So this is Terawak AI Robot Simulation by me, Aditya Talakanti. This is the table of contents that I'll go through. So I just gave you my introduction. So here on this slide, I want to pursue a degree in engineering, which is why I chose the AI plus robotics domain for the program. And then when me and my teammate were trying to find a project idea, we wanted to find an idea that would show how robots can be used to benefit the world, the real world. And we decided upon humanoid robotics because it's a growing industry in society, but there are certain issues that with like physical balance and movements and complex computer systems that are hindering its growth. So we created a kinematic simulation to show humanoid robots in real time, and we allow users to change the conditions and give commands. So the problem is that in today's society, there are extensive programming skills, graphic dependencies, and software required to simulate humanoid robotics. And many tech companies are working towards this as society becomes more advanced, such as Amazon. So in addition, humanoid robots struggle to maintain physical balance and perform complex tasks or movements in different environments. And lastly, public safety concerns are hindering the industry's growth because extensive testing is needed to deploy humanoid robots to perform everyday tasks for companies and people. And here is a picture of a robot struggling with balance. And then here is the different capabilities that robots currently have, and some time will be needed before they can actually be used to perform everyday tasks. So some real world insights are that this infographic, it shows the different parts of a robot that's needed, such as the computing, the different visions and sensors, the different actuators, and the processing systems that are needed, and the batteries. And with all these different parts, humanoid robots can often only be active for 1 to 4 hours before their batteries run out. In addition, this spectrum, it shows the reliability of robots as they get more advanced. So commercial robots like vacuums like Roomba, warehouse robots, or small factory robots, they're much more reliable and safe right now. As we increase like factory robots, they are they are generally still more reliable and are still used mainstream. But humanoid robots are largely in the research phase, and they still require more demonstrations before they can be used, and they're more expensive, and which is why they can often only be reliable for 30 to 90 minutes before needing human intervention. Changing or hidden objects in different environments can confuse a robot's vision and orientation sensors, such as VLA models, which causes them to fail instantly. Processing human environments requires massive sensor and data for humanoid robots, and that can strain processors. And lastly, current AI models cannot predict how a robot will be affected by changing friction coefficients. And this infographic shows that robots still need to be adjusted for efficiency and capability and AI and for human spaces and ecosystems before they can be used in industries. So the solution is an application called Terawak Core Labs or Terawak AI. It's an AI-guided kinematic simulation, and it lays the foundation for societal development because it operates on a serverless web architecture with the proper front ends and back ends. The simulation provides a visualization of a humanoid robot in a matrix-like environment that users can change and alter the conditions, and they can give commands to best fit their needs for research and see how the robot responds in real time. My application also contains information about the systems running it, and it educates people about robots in general, which can set the stage for further exploration. Overall, the application is accessible, user-friendly, and will help people find ways to approach emergency situations, such as in disaster rescues and unfamiliar environments, because they show how robots can respond. respond. And lastly, the simulation runs by connecting user inputs through API keys in a JSON format, and is supported by the large language model Grok. Here's a picture of the robot standing still in the simulation. Here is the different some of the different conditions that users can change in the left console of the simulation. And then here is a picture of the pipeline that allows it to run, which I'll explain more about later. And that's it for the presentation part. So now I'll demonstrate the application. You can see this, right?
Yeah, it's visible.
Okay, so here is the login sign up page of my application. It contains some preview information about it, such as it's a humanoid locomotion matrix. It bridges the gap between large language models and kinematics. There's some preview features like the different terrains, the different metrics, the hazards, and the different prompts users can give. So you can either skip the login and go directly to the dashboard, or you can create an account and with Google Auth. So I create an account and I'll log in here. So here's the dashboard of my application. There are some different metrics at the top. It's a live stream and a username if users create an account. So here are, you can change the different terrains. Right now it's on desert dunes, but I can change it to this one, Arctic or volcanic or industrial. And then you can change some different conditions like the friction. You can change the tilt angle, which you can see it shows the environment tilting. And you can also make the robot lean to one side. But if you go too far, then a system failure occurs and the robot resets. And you can also randomize the terrain. And if you need to, you can reset everything. So over here are some pre-validated commands that users can give. If I click nominal forward traversal, it'll appear in this traversal prompt over here. And if I click engage, the robot will walk. When it approaches a hazard, it'll slow down. So in order to clear the hazard, I can ask the robot to jump. And it jumped. I can also ask it to shift to one side. So I'm going to say shift left. When I do that, the robot shifts left and it clears a hazard. I can also speak using my microphone to say something. So I'm going to ask it to walk. And then it walks. And you can also ask it to stop. If the robot goes too far off the map, then the simulation will reset and an error will appear. And lastly, for the simulation page, there is a destination routing feature. So I'll ask it to go south and I'll say at a distance of 20 meters, and then I'll say avoid hazards. And when I confirm the destination and click and ask it to walk, it'll walk until it reaches the ending point of the destination path. So that's it for the simulation page of my application. If I go to the robotics and information page, this page explains some general information about robots, like the sensors, which are the eyes and ears of the robot, which includes LiDAR, ultrasonic, in order to calculate distance, measure temperature or terrain. The brain of the robot, this application, TerraWalk AI, it's powered by the large language model Grok and localized kinematic Mac to calculate step frequency, joint angles, and maintain the center of mass. It explains some information about the muscles of the robot, which are actuators and joints, such as electric motors or hydraulic cylinders. It explains the information about the power supply that robots run on, such as lithium-ion batteries or even hydraulics. It explains some information about the hands and the feet of the limbs of the robot. There's a visual that shows how a robot thinks and acts. So something in the world changes, it'll sense it using IMU or LiDAR. It'll plan, the motors will move, and then it'll act. It explains the difference between open loop robot and a closed loop robot. It shows how robots think very quickly, which reflects in the browser of the application. There's a visual that explains the anatomy of how a robot moves, which is called controlled falling for bipedal robots. It explains about step frequency, the support it needs, and how it needs to clear the ground. There are some questions about the different kinematics. If a robot needs to land its feet, then that's really simple. But if it needs to move onto a different object, it's much more difficult. The application shows different joints of the robot moving, like the hip, the knee, the ankle. This information explains about those and how the AI renders it in using physics. It shows the different types of robots, such as bipedal robots, which are humanoid robots, quadruped, vehicles, and then fixed manipulators, which are like manufacturing arms. It explains about the different sensors like IMU, LiDAR, and shows how they all combine into sensor fusion in order to make the robot function and see. And lastly, in this page, there is a glossary. There's also a AI chatbot that people can ask questions to. So if I ask it like, what is a robot? It'll output an answer. And lastly, there is an architecture and systems page, which explains how the simulation runs. So it leverages, the front end leverages WebGL via 3.js to manage the physics, and which replaces the heavy graphics dependencies that normally they would need in the real world to function. And also it's deployed on a versatile serverless, so using a Flash Python server, which allows it to run instead of needing like heavy computer setups. It explains about ZMP stability. So as long as there's a support polygon, as long as a ZMP stays inside the support polygon, the robot will not fall over. But if it does, then the robot will fall over, which is what the system failure error in my simulation reports. There's an equation showing how ZMP works. There's some information explaining how the sine and cosine functions in the code of my application. They are decomposed into X and Z vectors, which allow the robot to move. Now, this section in the page explains how user inputs. So Terawalk connects to the Grok API, and it's passed via the env keys. And so the backend outputs, the AI outputs a JSON format back to the front end in order to render user inputs. So the physics stays in the browser, but the reasoning leaves it. So the operator inputs voice or text, which is translated. Then it's sent to the front end, the Flask API, which is the versatile serverless. Then it's sent to the back end, which is the Grok large language model. It's the kinematic brain of the application. Then it's changed into a JSON format, which comes back and renders it in the application. And there's a client side, there's a server side, and then it's fast because it's a JSON format. There's some more information about the engine of the robots and how hazards are spawned and robots need to calibrate before they move around them. It explains what the AI does in the application between what the browser does in the application. And it explains how Versal deploys the topology, and there's some code showing that. There is an area that explains how users can create an account using Supabase and Google Auth using different passwords or credentials to log in. There's some more engineering notes about the different parts, like the telemetry, the HUD, which is a 3D space, the voice, and the canvas. And lastly, the future scope of this application could be, maybe there could be several humanoid robots in the same simulation. There could be a library of saved strategies for robots to move in different environments. Maybe there could be haptic feedback in simulation so that users can feel the impact forces. And lastly, there could be different obstacles and weather conditions in the application to increase the strength of the kinematic brain. And that's it for my application. So thank you for listening.
Okay. Yeah, you can now stop presenting. Yeah, firstly, the idea is pretty cool. I mean, all the UI and everything, it's really cool. Okay. The way the robot was just moving when the obstacles came in, and like, according to the terrain, how it was like bending and everything while maintaining the center of mass. Okay. That was really cool. I wanted to know, like, how did you come up with this idea? Like, okay, you're interested in robotics, but like, how did this idea like strike your mind?
So when me and my teammate were discussing in the meetings about what project we could do, first we after the meeting we sort of came up with a list of ideas and to see what we could do. Some ideas I came up with like a robot scanner that scans different things in society like recycling or traffic signs. My teammate came up with the idea of a sort of showing how the physics of a robot moves, and then he was addressing that robots don't struggle with balance in society, and that a simulation would show how they can move and how they can respond into different environments, because the terrain is a big issue in order to deploy robots, such as like disaster rescues. Maybe that could be a future plan for society, but different terrain would complicate it because that's what robots struggle with. And so we decided to create the simulation, and then our mentor helped us create the foundation, which is the simulation. And then we me and him we sort of me and my teammate, we went in different directions in order to implement different features. So I added like different features for people to change and how they can, and I added some of the pages about the system behind it and the information.
Got it. Um, yeah. Feedback about your PPT would be you can like add some numbers to it, as in like what are the different problems that you're trying to tackle? Who are the people who are actually facing, like the percentage of population that is actually facing this issue, and how can your solution can actually like benefit them, and how much risk can be avoided by using your product? Okay, that is something that you can include in your presentations. Now, other than that, the things that I liked was you had really nice infographics, okay, for explanation and all. That was really cool. Other than that, see, in UI, I'd suggest not to keep that big of an information, because there were so many sections, right? People would be more than happy if you could like include like a small video of it. They could just go inside and just see the comparisons or the learning things, right? It like people won't be going through that much information, right? So that is one thing. Other than that, all the tools, all the like features that you had, that were pretty cool. um Other than that, how accurate do you feel the current model is? Like, how much accurately is this working?
How accurately is it functioning when you ask the robot to move?
Yeah, like, are you pretty confident? Like how confident are you with the model? Sorry, the robot, how it is moving or responding to the terrains and everything?
I think there could be some improvements. I think maybe for the more difficult environments like the volcanic or Arctic, where there are like more hills or more rocks, there could be a feature where the robot has to like walk uphill and walk downhill or climb over it, because the robot cannot always walk, and that's something that society should work towards creating. And sometimes the simulation, I think there could be a few more movements that the robot can make, such as it could crouch or um, it could run. I mean, you can increase the speed, but maybe the animations could be a little more realistic.